All right. Well, thanks a lot for inviting me. Thanks for giving me the opportunity to present today. So before I start, just many thanks to my research group in Cambridge, the Cambridge Image Analysis Group. They are really indeed wonderful. And so without them, what I'm going to present would not have been possible. So thanks a lot to all of you. Okay, so and also please interrupt me anytime. Yeah, so I might have anyway too many slides. So if I don't get to the end, it's not a tragedy. Okay, so what I want to do is I want to talk about machine learning, in particular deep neural networks, as regularization procedures for solving inverse problems. I got interested in this maybe 4 or 5 years ago, really through a lot of papers that were coming out at that time that showed things that really we haven't seen before, I think. Kind of quality of solutions that haven't been possible before. Okay. And that is really because neural networks, as we have also seen in many talks this week, are just very, very good in capturing structure and data. And this is something that we can use in inverse problems to capture structures that we otherwise are not very good in modeling, structures that we want to promote in solutions to our inverse problems. So this is kind of the philosophy. What has also been quite apparent in these early works that served as a motivation was that deep learning really only works for solving inverse problems when combined with mathematical and statistical modeling. And here I really mean working in terms of working in practice. Working in scenarios where we have ill-posedness, working in scenarios where we have, like in practical situations. I work a lot with people in other disciplines on real data where we don't have a lot of training data available. And we use imaging often as a tool to actually look at something which we don't know how it looks like, things which for the naked eye wouldn't be visible otherwise. So it's hard to think of, huge amounts of training data that usually people in computer vision and so on have. On the other hand, in general, there is a lack of understanding of these type of approaches, and definitely a need, also of course linked to the second bullet point, for more mathematical scrutiny when developing these methods. And so one of the subsets of deep learning for inverse problems approaches that I have been particularly interested in is deep learning in the context of variational regularization models. So using deep learning as a component within a rather classical way to solve inverse problems. And with the hope to combine some of the mathematical framework that we get for free from variational modeling and functional analysis with plugging in the neural network where we actually need it and not anywhere else. Okay, so okay, so very briefly, because I think this audience knows this anyway, but just to set the scene, my talk will really be about linear inverse problems that, as they appear, for instance, in medical imaging, such as in computer tomography. And indeed, computer tomography, as I've depicted here in pictures, is the problem that will accompany us through the talk. Although everything that I will tell you is true for any kind of linear inverse problem. But that's the example that I'll focus on. And so that also shows you already maybe one of the challenges of applying deep learning to such inverse problems, because the typical framework is that we are measuring something that I call y, that is a transformation of physical quantity and image U that I want to, that I'm actually interested in, plus some random corruptions that I have in the data, just because of the physics of the acquisition. And so what I actually want to do when I start with measurements that look like this, that really live in a quite different space than the image, is to go from such measurements to an image like this. And so these transforms are usually kind of integral transforms. So these are global operations that we need to capture through our inversion process. The other thing is that inverse problems, and this is why mathematicians are looking at them, are usually ill-posed. And in the linear case, this is mostly because measurements are incomplete. In imaging, it's really because we don't have enough time, or because we don't want to radiate people too much, people or objects, when we image them. And we have noise in the measurements, and that's again, for instance, in computed tomography, it's related to the size of the dose that you apply when you image someone. Okay, so low dose measurements have higher noise than high dose. Okay, and so to counteract this, so basically we have an underdetermined problem plus noise. One standard way is variational, or well-postness through regularization, and one subset of this is variational regularization. And I think I can probably glimpse over that slide, because everyone here knows what variational regularization is. Is that true? Okay, maybe conceptually. So the idea is, okay, so this is my problem. I want to compute U from Y, and I can't do that just like that, because let's say I don't have enough data, and even if I would have, I have this noise here. Okay, so one way around this is to try to compute an approximate solution to this problem as a minimizer of an energy functional that usually features two terms. One is a data, so-called data discrepancy or data fidelity term that you can think of, and actually I'll only look at that, but doesn't matter, is some discrepancy that measures the discrepancy between the measurements and your model for the measurements. Okay, and then the second term is the term which now renders this as a well-posed problem, is my regularization term, that in most variational regularization approaches really adds additional regularity to the solution. Okay, so this is the one that picks from, let's say if this is an underdetermined problem, picks from the multiple solutions that might match the data, the one that you actually want. So this is where your modeling capacity mostly goes into. And the total variation, actually also because I'm going to show you some total variation reconstructions later, is one that has been really quite successfully applied to lots of inverse problems, also in practice. Yeah?
Just because it's a question about the so you consider this approach, you include this variational approach regardless of the regularizer, or the particular regularizers that you would call a variational regularization?
Well, okay, that's a good question. So mathematically, in the functional analytic setting, you would call a regularization something that if the regularization parameter goes to 0 and the noise level goes to 0 in a particular rate that depends on the regularization parameter, or the other way around, you should converge to kind of ground truth solution. Yeah? So to what in inverse problems you call R minimizing solution. So you should match the data perfectly in that case. So this is what in a functional analytic sense you call a regularized solution. But here you can think of it generally as any kind of functional that models prior information that you have, and that serves as a penalty to distinguish between good and bad solutions. Okay, and this variational approach actually has been extremely successful in many applications. And here, just anecdotally, from the kind of things that we have been doing in the last years, you know, these variational approaches, they appear in computer vision, they appear in digital restoration approaches, such as inpainting, which is something that's very close to my heart. And they appear in biomedical imaging, again, tomographic reconstruction, for instance. And also they even appear in things like classification of images, of a data set of images, where your regularizer models structure that you have in the data, and the fidelity term, for instance, could model some labels that you already have for some images in these data sets, for instance. Yeah? So it's a very, very rich framework, but there are limitations to it. And these limitations are really the reason why deep learning had actually a huge impact in inverse problems to date. And the limitations are just the fact that images, maybe I'll just quickly go to the next slide. I mean, depending on, so first of all, if you look at the variety of images that people might be interested in science or in real life in general, they're very, very diverse. So the structures that you see, the type of what is important, what is not important, and so on, really varies a lot. And that's one thing. And then even if you look at one type of image to model certain structures in images, I mean, think about textures that you have here in this histology image, for instance. It's very, very, very hard to just think about writing down an equation or a dictionary or something like this that might really represent those well. And going back to the total variation, for instance, it has been very successful because to a certain extent there are some commonalities, like something that people have agreed on, and why the total variation has been very successful is that edges in images are something that is very characteristic, not just because of the visual importance, but also because a lot of the time, these type of images that you see here are not just imaged because people want to look at them, but because they want to quantify something on the basis of them, like, for instance, to segment something and then do some further analysis with these segmented objects. And for that, image edges, seem to be very important. Anyway, still, this generality and this that total variation works across so many different applications also has its limitations, and that it's not the best thing you could do for each of those. And this is where data-driven approaches might come in handy. And here, this is just a teaser. Well, where I go back to computer tomography, and I show you 3 different reconstructions that match this data, in exactly the same way, but that has some very different qualitative properties. So one is the most basic reconstruction, the pseudo-inverse reconstruction, called with the back projection, that you can think of as the baseline kind of unregularized reconstruction. So you still see lots of noise in the image. The next one is total variation regularization, and then the last one is one that I want to talk a bit more about in this talk, is still a solution of a variational problem, but with a regularizer that is given and then is given as a neural network and trained with a certain strategy that I'll explain. Okay, and just to zoom in a little bit to show you, not to stick to small images, although the projector is not great, but sorry about that. I guess the online people have an advantage here. So This is total variation regularization. This is the solution with total variation regularization. What I show you here are just quantitative evaluations of the reconstruction. Again, that we have seen in earlier talks. I think Gabi also showed some in her talk on Monday. So this is the peak signal to noise ratio. This is the structure similarity index measure. And in general, the higher they are, the better. This is what you get with a learned approach. And this is now the kind of ground truth from which we have simulated these measurements. Yeah? So if I just briefly go back, this is the total variation. So this is a prototypical, I would say, non-learned approach for tomographic image reconstruction. And this is now the difference to if you involve learning. So, you know, and this approach, what we have worked on, this adversarial regularizer approach, is not even the best deep learning thing that you could do. Okay, and still it almost, you know, perfectly matches the data. It can never exactly match the data because that, you know, this is an underdetermined inverse problem. This could not be, right? Okay, so right. So how have people thought about doing this, involving deep learning into solving inverse problems? And there are different paradigms that people have thought about. The first bullet point I will skip because I think it's not very interesting and also not practical. The first bullet point is just that you train a neural network directly from measurements to reconstruction, forgetting all about the physics that you know about the model that you have for the data, except when modeling maybe the neural network. Okay, so this is these are so-called fully learned models, but they weren't very successful because they're just impractical. And I can say more about that if you want. Then I'll say a little bit more about those two on the next slide, and then the main thing I want to focus on is this learning the regularizer. Okay. Yeah, and maybe also just to say that here are a few references. They're not at all complete because it's really exploding this field. Just a few, you know, pointers. So if people want to go back to these slides, you can find out more. Okay, so two very, very successful approaches for deep learning for inverse problems are what I call post-processing, and the other one learned iterative reconstruction, or what people also call learned unrolling. Okay, so here, first of all, with the learned post-processing, the idea is as follows. So one of the difficulties for training a neural network to go directly from measurements. Okay, so this is an example for magnetic resonance tomography, but it doesn't matter, where the measurements are Fourier coefficients of the image you want to reconstruct. So the difficulty in going using a neural network to go directly from measurements to an image is that this is a global transformation. And hence, if you train a neural network directly to do this, you need fully connected layers. And in inverse problems, we usually look at really, really large data. So that's why this is unfeasible. And so one other idea is to say, okay, let's do a very simple kind of baseline reconstruction first, like filtered back projection, for instance. Yes?
Why do you need a fully connected layer?
Because it's an integral transform, right? So in order to know what the pixel here looks like, you need to know everything from the Fourier transform. It's not that you can localize things. We can talk later, but it's just because the image is, I mean, the Fourier coefficients are an integral over the image, and that's why you need to basically touch every part in the image to explain the Fourier transform. So that's the idea.
Still, I mean, you can factorize the Fourier transform and neural network is also some kind of factorization. So of course you have to figure out like how precise it is the structure, but still still, I mean, you could probably model it as not fully connected.
Maybe people have done this, I don't know, but these fully connected, these fully learned models didn't, I mean, they no, I mean, one was really, so I don't know, we can talk later about this decomposition into sparse filters and so on. On the one, so once, I don't know whether people have done this. Hence, they have really looked at these fully connected layer networks, which were just became computationally unfeasible. And then also, and this is, you know, this I think is the biggest reason not to go for that, is that you really throw away the fact that it's a Fourier transform. Maybe with your approach not, because intrinsically you use this to do this decomposition, but there is no component in these neural network solutions, usually for these fully learned approaches that use the fact that it's Fourier transform that they're trying to model.
You know, it's Fourier transform,
you should somehow use it. Yeah.
But I think maybe one way that just
yeah, no, it's okay.
But if you could do, for example, do a Fourier transform, and use convolutional layers on the Fourier transform, which is something that in speech people do that. Like they use like synonyms on the what they call
so basically, this is more or less what is done more or less in this post-processing, because there you just say, so there you just say, okay, these are Fourier measurements. I do some zero, so usually they're underdetermined, so you have some missing, so you do zero padding, and then you invert the Fourier transform, and that, which gives you kind of a crappy reconstruction, but at least you're in image space, and then you use a neural network, and most of the time people use the UNet because of its multi-scale structure, I guess, that is good for regularizing images, to clean up the mess and then get a good reconstruction out. So this is kind of there's a two-step process. Okay, the first invert and then you regularize. Sorry, and then we'll go on now a little bit, because otherwise I don't come to the adversarial regularizer. The learned iterative reconstruction or learned unrolling is intertwining the inversion with the neural network, with the regularization of the neural network. In the simplest, you know, in the simplest setting, let's say, or easiest explained is, imagine you have a variational model, you write down gradient descent for minimizing this. And let's say you write down the first 10 steps. And then what these learned iterative reconstruction people do is they say, now in these 10 steps, I forget about the underlying variational model, and I parameterize each of these 10 steps with a neural network, and I keep the fidelity term. I'd maybe also do some neural network stuff with the fidelity term, but I have the forward operator in these iterations. Okay, and then I just do 10 such iterations. So, and these learned iterative, learned unrolling approaches are, I would say, one, you know, kind of the state of the art for solving inverse problems with deep learning nowadays. Because they perform really well. The disadvantage is, though, that they're mostly a black box. And actually, I mean, Gabi didn't talk about this, but Gabi has, you know, one of the papers where she looks at, for instance, proving fixed point convergence for these type of approaches. And the disadvantage is still that, you know, you converge to a fixed point, but you don't exactly know what this fixed point fulfills. But at least you have some, you know, some kind of guarantees. Okay, but overall, the framework for these type of approaches for solving inverse problems is really that there are almost no theoretical underpinnings. I mean, none of you asked before whether, you know, what does it mean if something is a regularization? It's not at all clear for these approaches whether they are really regularizing the problem. And I look forward to actually also the next talk, because I think Martin will also talk about, you know, what we want to impose on these deep learning solutions in order to, or what does it mean for deep learning solutions to be robust. Interpretation is, of course, also another big issue, because if you send your measurements through such a neural network and you get out something, and you have these millions of parameters in between, it's not so easy to know what has happened. And you know, asymptotically, some things people can say, if, for instance, these learned iterative schemes are trained with an L2 loss, then what you converge to is the conditional mean in the infinite data limit. But this is also the question, how useful is this, right? Because eventually you don't know how far you are from that. Data consistency is also a big problem. I mean, think about this, for instance. Here you don't know whether, I mean, here they do a trick actually, that you have data consistency, but eventually you don't know what comes out here is actually really in the range of your forward operator. And usually also these type of approaches require lots of supervision. There are not so many of these approaches that can deal with small supervision or even no supervision at all. And again, I think Gabi's talk has been very interesting at the beginning of the week, because she showed one idea using patches, for instance, to get around this. Okay, but I want to talk about learning a regularizer. And the idea is really, as I said at the beginning, that you know, you can approach this framework of using deep learning for solving inverse problems in various ways. So how I want to do it, I want to say, okay, I want to remain in a framework that has been proven to be very successful for solving inverse problems, where we understand a lot, where we have a very beautiful mathematical framework around. And I want to use really very directly the deep network only where I think it makes sense, namely for the regularizer. Okay, because I think this is the part where we always had trouble in coming up with good regularizers, and this is why hundreds and thousands, 10,000s, 100,000s of papers have been written to propose newer and newer, more and more regularizers. Okay, because it's not so easy. Okay, so that's the framework. So I stick to the variational framework, and now the underlying statement here is, what we want to have in mind is, we don't want to learn how to reconstruct, because in the end we use the variational model to reconstruct, and that's very different to the other approaches, right, where we really learn the reconstruction directly. I want to stick to the variational model and just learn the regularizer. Okay, and that's now joint work with several wonderful people. So the person who started this was Sebastian Lunz, who was a PhD student of mine, who unfortunately went into finance afterwards, but he's happy, it's fine. And the person who is now working the most on this is Shubha Mukherjee, who is a postdoc with me, actually soon going to Bath for a lectureship. And then Marcello Carioni, who is in Twente. Søren Dittmer, who is in Bremen as well as Cambridge. Ozan Öktem, who is a colleague of mine from KTH. And then Zach Shumyalov has been an amazing undergraduate student who worked with us for 2 summers and is now starting a PhD this coming autumn. Okay. So, so I want to learn a regularizer. Yeah? So now the first question is, how do I do this, right? I mean, the first thing is, okay, I represent my regularizer as a neural network, okay? And then how do I train it, right? So what's my training criterion to get a good regularizer that works in this variational setting? And for that, if you look again at the variational setting, you know, what the regularizer should do somehow is it complements this discrepancy term by saying, okay, on the one hand, I want to compute a solution that matches the data. But then from all these solutions that match the data, I want to pick the one that I like, right? I want to pick the one that is most probable under all the information I have about the problem I want to solve. So this really, again, models the prior information I have about solutions that I want to compute here. And in this variational setting, this is really done by saying the solutions I want to discourage for those, the regularizer should be large, right? And so think about the total variation. The total variation doesn't like oscillations, and so it will penalize them. And on the other hand, it should favor the kind of structures that I want to preserve in my reconstruction. And again, for the total variation, these are the edges. The total variation is known to be good for preserving edges. And now I don't want to do this in this kind of modeling way, but I want to do it by representing the images that I want the regularizer to penalize and the image that I want the regularizer to favor in terms of two data sets. Okay, so I have a data set that I call the good guys that should be images that feature structures that you want the regularizer to like, okay, to be small for. And in the case, and this depends what you do there, depends on the application. In the case of computed tomography, for instance, what you can do is to say, okay, I have maybe some phantoms that I've acquired with very, very high dose measurements, and these are my good guys, okay, for instance. And then the bad guys are the ones that I want the regularizer to penalize. And so these could just be reconstructions from a baseline method that you want your variational model with the learned regularizer to improve upon. Okay, and in the setting where your inverse problem actually has a pseudo inverse, you could take the pseudo inverse as your baseline reconstruction, again, which is in the case of computed tomography, filtered back projection. Okay, so that's the philosophy. And now, how do we put this into an optimality criterion? Well, let's just first look at this, which then will turn out that is actually the Wasserstein distance. But so the idea is, maybe I should just fix notation quickly. So the good guys, I call the distribution, the underlying distribution of the good guys, I call them PU. And the distribution of the bad guys, I call them PN, where N stands for noise and maybe U stands for solution I want to compute. Okay. And so now I want to just put into a formula what I just said before, right? So I want to compute a regularizer. I want to train a regularizer that if I feed the regularizer with samples from the bad guys, from the noisy reconstructions, I want the regularizer to be large, right? I'm maximizing here. And if I feed the regularizer with samples from my, let's say, ground truth distribution, or the desirable, the distribution of desirable images, I want the regularizer to be small. Okay, so that's the idea. And then I add this additional one Lipschitz constraint, which will, come back handy later on when you want to do this analysis, but in particular gives you the nice relationship with the one Wasserstein distance. And I mean, the reason, also to be honest, the reason why we discovered this was that the initial idea was, okay, we want to train the regularizer in this kind of discriminatory fashion, right? So we want the regularizer to kind of look at these bad guys and these good guys and to differentiate between the two. And this is where, if you have studied something in machine learning, immediately these generative adversarial networks come to mind, right? Because they always have this discriminator and the generator. And for the discriminator, these Wasserstein GANs have been very successful because they allow this training of these generative adversarial networks in a more robust fashion. Okay, so they're easier to train and so on because they regularize the network more. And anyway, so we ended up with this, and it turned out to actually work quite well. The nice thing about that is also that for our training set, the good guys and the bad guys, they don't need to be paired, right? And this is very nice if you want to apply something like this to real applications. Again, really real applications with real data, where you don't have matched good guys for the data that you have measured, right? So you can come up with the good guys yourself, or, you know, with something that is close enough to what you want to compute. Where? Here, you already jumped ahead. Yes.
Oh, sorry.
No. One. But you mean this, right? Well, it's just very briefly here. It's just okay. So here, of course, we are not looking for all one Lipschitz regularizers, but now the parameterization comes in. So now we replace this with neural networks, right? So we say my regularizer R that eventually I want to use should be given by a neural network that maps from this image space to R, and because of reasons for analyzing the variational model, eventually we also add this L2 square term so that you get a bound from below. And once we do this, what we actually train, so what you refer to is what we actually optimize, is this loss function here, where we take the one Lipschitz constraint and approximate it with this penalty term. Okay, where here what you basically do is you penalize such that the gradient of your neural network should be the size of the norm of the gradient should be approximately 1, and the star here I guess just means that you for evaluating this gradient, you look at all kinds of interpolations between PU and PN samples. Okay, this is where you evaluate the gradient. This is not so important actually. So, okay, so this is how you train it. And then maybe one more thing is that now the question is, how do you exactly parameterize this psi? What kind of neural network do you use? And so generally, you know, you can use any neural network you want. Again, if you think about that you want to use it for regularizing images, convolutional neural network is the way to go. And then you can do more if, for instance, you want to have more structure. You want to impose more structure onto your regularizer. And one structure that we tried out, because computations are just so much easier, and because also mathematically you get more results, is that to impose actually convexity on this regularizer psi. And this is something that maybe some people here have heard about before, are these input convex neural networks. And I can, you know, I have a slide on the parameterization of these neural networks of how to get them actually to be convex, but yeah, I need to go on now a little bit. Okay, so hence we basically get two regularizers depending on our parameterization. I always call general the adversarial regularizer, the one where I don't impose anything, I just use an off-the-shelf convolutional neural network, and the adversarial convex regularizer will be the one where I use this input convex neural network. Okay, let me just see if I can say this here quickly. Just a few basically intuitions of why something like this might be a good idea to, you know, why training a regularizer like this might be a good idea if you later on you really use it as a regularizer within a variational model. And so one of the things that you can show is that if you start with your distribution of the noisy reconstructions, yeah, okay, and you push them forward, let's say, by doing one gradient step along your trained regularizer, okay, with a certain step size eta, and you create a new distribution, P eta, that now encapsulates all these pushed for, you know, these one gradient step away from the noisy samples distribution. Then you can show that actually this one gradient step brings you closer to your solution of the desirable guys. Okay, so this is maybe, if you think a little bit about it, it's more or less trivial, but it gives you a nice intuition of why something like this might make sense. Okay, so let me jump over this. I can say more about this later. And I want to show you some results. And by the way, this also, I thought also that I show a little bit more about the convex stuff, because Felix had in his talk also this question about whether convexity or non-convexity, when, when does what make sense, or when, is convexity or is non-convexity always the way to go. So anyway, so this is now the summary, this is the recipe. So the idea now is we create, in order to solve an inverse problem and to get a regularizer for this inverse problem, the one thing we need to do is we need to create this training set of the good guys and the bad guys. And then we train the regularizer. And then we take the regularizer and plug it back into the variational problem and do everything as we have done it before when we solve variational regularization problems, right? This regularizer will be, apart from this little addition of the L2 squared term, will be normalized. So you still need to do some, selection of the regularization parameter and so on and so forth. The nice thing about this now is that you stick to a variational problem, and so you get basically for free from the framework you are in, this variational framework, you get for free all the nice properties that you want from an inverse problem solution. Okay, and I mean, just very briefly, because this is again very, very standard, you get a bit more with the convex regularizer. And in particular, what you, in this generality at least of the non-convex regularizer, you cannot show, or you can show only in a weak sense, is that this is actually a convergent regularization, right? So this is something that you get with the convex version. And of course, also solving the convex problem in the end is much simpler. Okay, so yeah, one more thing. So one thing that is, of course, a little bit annoying and that I actually haven't mentioned yet, and this is also why people, or maybe let's stick there, why people have been looking at getting rid of variational problems, is that in the end, I still need to solve a costly optimization problem every time I want to compute a solution to my inverse problem, right? And with all these other deep learning solutions that I mentioned before, once the network is trained, it's just an explicit evaluation of vector matrix multiplications, which can still be costly because it is usually large. But it's not that you need to invert stuff again. You need to solve systems of linear equations or whatever to actually compute your solution. So this is a shortcoming. And so one of the things that we thought about, not just because of this, but also because of one thing that I will mention now, is the idea, and sorry, the slide is quite busy, but I'll explain it in a moment, is the idea to think about whether we can do unrolling on the one hand to get a better regularizer, but on the other hand also to, while training the regularizer, also get a generator, that a neural network that computes the solution. And yeah, and so this came very naturally, actually, already when we looked at this for Sebastian, but at that time we actually couldn't get it to work. Through the fact that before, if you think back, before, what's the difference to how we train this regularizer to what you know from GANs, right? From GANs, you know that what we do here is basically the discriminator part of a generative adversarial network. For GANs, what you usually would have is that there is a generator that tries to fool the discriminator, right? And that is how we train it here, static, right? Because these are the bad guys. Does it make sense? Now, that comes very naturally to then say, okay, let's replace the bad guys by a generator. Okay, so that's basically the idea. So now you train two networks like in a GAN setting, a generator and a discriminator, and use one as a regularizer and the other one as something that you might want to use to compute in the end your regularized solution. Okay, and that then, you know, the generator then would offer a fast and efficient reconstruction. Yeah, let me jump over this. Let me show you some results, okay? So, okay, so I want to start with actually the setting that we started out with, the computer tomography setting, with a sparse view geometry, which means that I have an underdetermined problem, okay, because I'm leaving out every other angle more or less, okay? So I'm not measuring all the angles for my tomography problems, but I'm leaving out some. And then I also add noise to the measurements, mimicking some kind of low dose setting. And what I'm now going to show you, and maybe just to say, I mean, you can read all this kind of maybe almost standard, but I mean, we used an OpenCT data set and we trained on 9 patients and tested on 1, okay? Okay, and the different reconstructions I will show you now to compare with is filtered back projection. This is just our baseline reconstruction, right? This is basically represents the samples we had in the for the distribution of the bad guys. Total variation regularization reconstruction. Then I'll show you the adversarial regularizer reconstruction already with this last update, okay, where I used the generator to make the regularizer even better, right, to challenge the regularizer more and more. Then I'll show you the adversarial convex regularizer reconstruction, and then I'll also show you, because I said at the beginning, these learned iterative reconstruction approaches are really kind of the state of the art for deep learning for inverse problems. So I'll also show you that. Okay, the one example of this, which is called learned primal dual. The difference between, again, just to say, because these are my 3 learned approaches, the difference between this one and our adversarial regularizers is that the learned primal dual is supervised, right? So also need to take this into account. Okay, so, right, I can quickly go through because this is actually something we've already seen. This is the same example I showed you at the beginning. Total variation regularization. This is now the reconstruction with the convex adversarial regularizer. Okay, so there is not so extremely much advantage with respect to total variation regularization. Okay, and you know, this is something maybe one can talk about later, is because these input convex neural networks are not very expressive. Okay. This is what you get with the non-convex version and with the one that has been challenged. And this is what you get with learned primal dual. Okay, so there is still quite a gap here between the two. But again, the difference really for me is, first of all, this is, you know, practically easier to apply because we don't need paired data, and we get a reconstruction that we can to some extent interpret. That matches the data, I mean, because we solve a variational problem and we get some additional guarantees from there. So the last example I want to show is now, I want to make it a little bit tougher for these deep learning approaches. And I want to look still at computer tomography, but at the limited angle problem. So the limited angle problem means, before I said, I look at a sparse view geometry, which means I leave out every other angle. Okay, so this is basically just saying I have a coarser, view onto the measurements, right? Now I really say I have 60-degree angle completely missing, from which I don't see anything of the object that I'm imaging. Okay, and I do the same comparison as before. So this is just to show you what limited angle means. This is simulated, and here you see exactly, if you have this amount of angles missing, you see the region where you don't see the object, right? And so this is necessarily that there needs to be something there, right? Okay, now, did I jump? Yeah. Okay, so how does it look like in this case? And on the left, I keep plotting the ground truth. Yeah? So this is filtered back projection, and again, you see exactly where the angles are missing, right? So you see that here we have problems because we haven't seen enough of the object from these directions. This is what you get with total variation regularization. Okay, so maybe the difference a little bit to filtered back projection really is that the total variation differentiates more between the noise and the actual structure, and so you know, it's maybe easier for a non-expert to interpret, and also for any kind of quantification method. Again, this is much better than the noisy version. This is what you get with the adversarial convex regularizer. Okay, so here maybe visually, I don't know, it's hard to say actually. You get maybe a little bit more of the texture. Okay, and quantitatively we are, I mean, 2 dBs higher, but I think the main thing maybe is that you see a little bit more of the underlying texture that you don't see with TV. This is what you get with the non-convex version. Yeah. And so here you see that. So just going back to Felix's question about convexity versus non-convexity. So this is, you see that for things which are, I mean, in this case, it's also a very specific inverse problem because you really have a huge amount of information missing, right? The non-convex version kind of is overdoing it. It's trying to overcompensate for the fact that, because remember the regularizer is trained to differentiate between this and this, right? More or less. Yeah. And so it's trying to overcompensate for the fact that it knows that these kind of artifacts shouldn't be there. And so it's trying to eradicate those by adding something that is kind of orthogonal to that. I mean, intuitively, I don't know if it's true, but somehow this is what you get. Yeah? This is what you get with learned intuitive reconstruction, which, in my opinion, is the most boring one, because while in the first case, I think learned intuitive reconstruction would have been your go-to solution, in this very, very ill-posed case, it actually invents stuff, right? It really, so it does what a neural network does, right? You know, where there's no data, it tries to put something. And in particular, actually, even in the parts where the limited angle actually shouldn't affect the reconstruction, it does strange things, right? Here, even the body shape changed. And here also some of these stuff, right, has changed. While in the variational, I mean, even in this one, although it's kind of horrible, but even in this one, you still see that it's actually consistent with the data, okay? It's just not a very good prior. And this is just to summarize again, right? So I think that we really just need to keep in mind that we can only go to a certain limit with these type of approaches. And if we think that an approach does magic, it probably does, and we need to be careful, right? That actually makes sense. Okay, let me skip the extensions because I think I'm running out of time, and just say a few takeaway messages. I think really, I still think that deep learning has a really important role to play for inverse problems, for modeling prior information. And we are not yet there to do everything perfectly, but we are getting there. Perfectly in the sense that we have to find a good compromise between robustness, mathematical robustness, and performance. And there are lots of open questions. I think for me, the most interesting open question, and something that I think people in inverse problems should be focusing on, is where inverse problems have an impact is in applications, you know, where we use imaging for science or for medicine or whatever, right? And so if neural networks, for instance, would allow us to image faster, to image with less radiation, to image with cheaper scanners, with smaller scanners and so on, and still get similar images back, I think this is really where this can have a huge impact. But such convincing use cases, I think, still need to be worked on. So this definitely needs to be done. Okay, and I thank you very much for your attention.